Here are the solutions to the 3 problems I assigned yesterday. The first is the AP problem from page 30, number 79, and then on page 215, numbers 13 and 16 I'll go over. All right, so looking at this problem, the graphs of the derivatives of the functions f, g, and h are shown above. So these are all of the derivatives. Which of the functions f, g, or h have a relative max on the open interval from a to b? So we get a relative max when our derivative changes from positive to negative. Because when this happens, this means the function changes from increasing to decreasing. That's the only way we'll get a max. If our function increases and then decreases, then we get a relative max. So this is where the slopes of the tangent lines are positive, and then it becomes negative. So let's see where this happens. So for our first graph, right here, again, this is the graph of the derivative. So our derivative stays negative. It's below the x-axis. It's still negative here. So it changes from negative to positive. So right here we'll say derivative is negative. Then it changes to positive here. That means our function will be going from decreasing to increasing. So it doesn't happen here. But on the other side, now we're positive, and we change back to negative. So it's going to happen here for sure. In our second graph, our derivative is negative, and then changes to positive. We need it to go from positive to negative, so it's not this one. And in our third graph, our derivative is always positive, so it's definitely not this one. So the answer is A, the first graph only, because we see our derivative right here changes from positive to negative. All right, so now let's take a look at number 13 off of page 215. And here we're designing a poster. We're designing a rectangular poster to contain 50 square inches of printing with a 4-inch margin at the top and bottom and a 2-inch margin at each side. What overall dimensions will minimize the amount of paper used? So let's go ahead and draw. This would be just the poster that's printed before the border's in. And we know that this area is going to be 50 square inches. So let's go ahead and say that this, like the length right here, would be X, and then this would be Y, because now we want to put a border around it. So we know from here to here we're going to have 4 inches at the top, 4 inches at the bottom, and we'll have 2 inches on either side here. So the spot right here in the middle has the 50 square inches. I'll just write this inside. So that means the area of the inner rectangle will be calculated by just multiplying x times y. So 50 would equal x times y. And we'll come back to that because that's going to be a helping equation here. But the question is, what overall dimensions will minimize the amount of paper use? So we're going to say the area of the poster plus the frame. So now if we took y, which is just going across here the width, we have to add 4 onto that. So that's going to be a y plus 4, would give us our whole distance across. And then the length of this poster, or the height of the poster, depending on how you look at it, from here to here, would be x plus 4 plus 4, so this will be x plus 8. So just like with all of our other problems, we want to get this all in terms of one variable. So now we're going to go back to our helping equation. We'll solve it for y. So y would just equal 50 over x, and that's what we'll substitute in here. So now we could say we have our area in terms of x only, which will become 50 over x plus 4 times x plus 8. And we'll go ahead and just multiply all this together. So 50 over x times x will just give us 50, Then we'll have 400 over x as we multiply the outside terms, and then 4x plus 32. And we can combine our constants here. So we'll say 82 plus 400 over x plus 4x. That's our area function. We're trying to minimize area, so we want to find the derivative of our area function here. Derivative of 82 will just be 0. We could think of 400 over x as 400 times x to the negative first. Actually, I'm going to take the derivative of 4x first, so that'll just be a 4, and then we'll get a minus 400. And it'll really be x to the negative second, so we'll put it over x squared. So there's our derivative. Then we'll ask ourselves our two questions about this. Where is it equal to 0? Where is it undefined? All right, so we had definitely seen a couple equations set up like this. What we first want to do is just multiply throughout by x squared. So we get a 4x squared minus 400 equals 0. Add 400, divide by 4. And we only want a positive value here, so x is going to equal 10. Where will it be undefined? When x is 0, but we can't allow that to be a dimension, so we'll just say never, since x has to be greater than 0. So now we're going to do the second derivative test for extrema. So this will become negative 400 times x to the negative second. So we will get a positive 800. Be times x to the negative third, or we'll just say over x cubed. And then we'll evaluate when x is 10. And that'll be a positive value. Therefore, we are concave up around x equals 10, and we have a relative min at x equals 10. So that justifies our work. And again, the question is, what overall dimensions? So the width was the x plus 8, and x is 10. So we will have 18 inches, and we'll call it the length. And that was, we go back up to the top here, 50 over x plus 4. So that's 50 over 10 plus 4. That'll give us 9. So the overall dimensions to minimize the amount of paper used would be right here. Okay, number 16 is a lot like number 3 that we did off of the in-class example sheet. So here again, we're designing a can. It's asking, what are the dimensions of the lightest open top right circular cylindrical can that will hold a volume of 1,000 cubic centimeters? So we're going to draw, here's just a picture of our can. Now we have no top, so we're not putting any material on the top. So that's the only difference between what we did in example 3. But here's the formula for surface area. Notice it's not 2 pi r squared because we're not including the top circular part of this. So it's just pi r squared. And again, if we cut this open and rolled it out, we would have the circumference become the length of this rectangle and then the height, so 2 pi rh. Our helping formula is the volume. So again, volume of a right circular cylindrical can is going to be pi r squared times the height. We'll set that equal to 1,000, solve for h because we want everything in terms of r. And we're trying to minimize the surface area. So everything else pretty much plays out the same way our in-class example did. So I'm just substituting the h right here and then simplifying. So we end up getting the surface area function is pi r squared plus 2,000 over r. And then we'll go ahead and find the first derivative. which we would get 2 pi r minus 2,000 over r squared. And we'll ask ourselves our two questions. Where is this first derivative equal to 0? Turns out to be the same radius that we got for our other in-class example. And it'll be undefined when r is 0, but r has to be greater than 0. Now we can go through the second derivative test for extrema and evaluate when r is equal to 10 over cube root of pi. That would give us a positive value. Here's our second derivative, which indicates we're concave up around this r value, so we have a relative min. And all we wanted to know were the dimensions, so I just substituted this in to find h. Turns out h is the same dimensions, same value as r. So those are the dimensions of the lightest open-top right circular cylinder.